the last week, okay, and you got used to your routine of lectures. This week will more or less be similar to last week in terms of number of lectures. Only you will see that as we get into the second lecture of each topic, the subject will get slightly more technical for you, and level of difficulty of assignments, etc., might increase a little bit. So it's all part of the learning process to get used to it. Also, this is a good time for you to, sort of fall into a good routine yourself, a good personal timetable. Make sure you have, more or less few do's and don'ts established for yourself, like you have enough hours of sleep before your morning lectures, but at the same time you have also organized your day into a routine wherein you have enough time for self-study, revision of the lectures, doing the assignments. Yes, I know some of you will have doubts since the assignment that I sent last week. We will discuss about that assignment in the later half of today's lecture also. I have sent you some hints also. They might be enough, they may not be enough to solve all the questions. It depends, okay? But don't worry. As you would have seen in the hints that I have sent, last week's assignment, it had to be solved mostly by just using the general concept of average rate of change, and very simple principles in mathematics like ratio and proportion, etc., can be used. Don't have to use differentiation at all anywhere, because I haven't taught differentiation yet. Okay, today's lecture we will learn about differentiation and the first part of basic calculus, and from there on, the process of differentiation can be used for doing these type of questions also. But in the assignment that I had given last week, the first assignment, you were just expected to use simple concept of average rate of change and ratio and proportion and graph principles and things like that to solve. Okay, so anyhow, I will discuss some of the questions in the next half of the lecture also. But let us begin today's session with some concepts in basic calculus. Okay, so this will be session number 2 for us. Okay, so in the previous lecture, we were looking at two important concepts related to distance and time. We saw that distance and time, or displacement and time. We saw that average speed this was defined as the distance covered upon the time interval. So this is defined for a specific time interval. So let's say that is delta t equal to t2 minus t1, or t equal to t1 to t equal to t2, this kind of time interval. So that becomes the distance covered in that time interval divided by the time itself. Okay. Whereas the other thing, the instantaneous speed, we saw that this is the more tricky one to define, because this is defined for an instant, or it is defined at an instant of time. Let's say t equal to t, and this is defined again as delta s by delta t, but under the condition that delta t should be very small. So it is the distance traveled divided by a time interval for a very small amount of time interval. And we had understood this more from a practical perspective in physics. And for example, if your speedometer is making a reading of the distance traveled, in the case of measuring instantaneous speed for a moving vehicle, so it calculates the distance traveled in a very short interval of time. For example, it might be able to calculate it for an interval of something like 1 microsecond or 1 millisecond or something like that. And depending on the shorter the interval of time for which it is able to calculate that distance traveled, the more accurate the measurement of the instantaneous speed is. Okay. Now today we will take this idea forward mathematically, and we will come to a more precise or more exact definition of instantaneous quantity. Okay. So, but before we establish that, okay, we will talk a little bit more in the language of mathematics. Okay. So we will talk about the language of functions and rate of change in context of that. Okay. So we will make these definitions for rate of change more general. It's not going to be applied only to the situation of instantaneous speed and average speed, but rather it will be defined for a more general definition, okay, between or general relationship between any two physical quantities. For example, we know that force is equal to rate of change of momentum with respect to time. Okay. Or we know that acceleration is equal to rate of change of velocity with respect to time. Okay. Or in future we can learn things like electric field is equal to the rate of change of potential with respect to position, etc. Okay. Or the electric current is equal to the rate of flow of charge with respect to time. So it can be the rate of change quantity, or the concept of rate of change might apply to any two physical quantities which are related to each other. Okay.
Sir,
Yes.
so rate of change and gradient is same.
To a certain extent, you can say. It's a good question you asked, Beta. So gradient is a term that we generally use more in terms of a graph. Like we say, slope of a graph at a given point of time is like the gradient, and rate of change is more when we use it in context of with respect to time. No, but
Okay, sir.
yeah, you can say that there is a relation between the two quantities. Gradient and rate of change are very much related to each other, and we can use them to a certain extent interchangeably.
Okay, sir.
Understanding? Okay.
All right.
Okay. Okay. So before we get into rate of change, once again, let's understand what is a function. Can anybody tell me what is a function? Have you heard the term function before? I mean, in maths, obviously we all have heard the term function generally in English language. Or can you give me an example of a function? Anyone?
So we describe it as f of x.
Sorry, Beta, can you speak a bit louder?
So we define it as f of x.
We define as f of x. So basically, what does the function do? What is the purpose of the function?
To represent an equation.
Yes, very good. It represents an equation. And what does that equation connect? How many terms are there in a function?
A polynomial equation.
Polynomial equation is an example of a function, right? That's true. So in polynomial equation, how we write something like this, that y is equal to, let's say, some constant plus another constant into x plus another constant into x square plus another constant into x cube. This kind of a series we write going up to any power x to the power n, right? That's the general example of polynomial function, correct?
Yes.
Okay. So in this, what we are doing, we are establishing, see, all these things, a0, a1, a2, a3, these are constants. So what is doing, but what about x? X is a variable quantity, right? And what is y? Y is also a variable quantity. But the difference between x and y is we have to select some value of x arbitrarily. That means without any reference to anything else. Independently, we can select some value of x. But once we have done that, the function will give us the corresponding value of y. So we say that y becomes dependent on the value of x. So for example, here, if I take y is equal to, let's say, 3 plus 2x plus x square. So this is a specific type of polynomial function, which is called a quadratic function. And its power is up to 2. Yes, Daksh, you are having some doubt, beta?
I didn't really get the definition.
You didn't get?
What is function in math?
Yeah, I'm explaining that only. I'm coming to it. I haven't defined function yet. Okay. You're understanding what is polynomial, right? This equation above. Yeah. So now see, an example of a polynomial function is this one. It's a quadratic function where the value of A0 is equal to 3, the value of A1 is equal to 2, the value of A2 is equal to 1, and after that there are no more terms. So the maximum power is 2 for x. So now what this equation is doing, this equation is establishing a relationship between x and y, such that if I take any particular value of x, then I will get the corresponding value of y from it. So if I take x as 0, for example, you can see that y will become equal to, so if I take the value of x as 0, it implies that y's value is 3. If I take the value of x as 1, it implies that y's value is how much? Its value is 6, and so on and so forth. If I take x as, for example, minus 1, then how much y is becoming this time? Y is becoming how much? 4 minus 2, right?
4.
So it's becoming 2, so on and so forth. So what it does is, it gives you the relationship between two variables, where one of the variables is what we call independent and the other variable is what we call dependent. So the definition of a function is that it's a mathematical equation, okay, which defines the relationship between two variables, let's say x and y. So it's an equation or a maths expression to define a relationship, okay, between two variables. So in sign language, in mathematical sign language, we write it as like this. This will be, this term or this kind of an expression will be read as y is a function of x. So here the quantity x will be what we call an independent variable, where x is an independent variable. So independent means that there's no dependence on anything else to select the value of x. The value of x is selected independent of the value of y or any other consideration. Okay, so where x is an independent variable, whereas the value of y is the dependent variable. And fx is the relationship that defines y as a function of x. Okay, so in mathematics, it's a convention that we always use the term x for the independent variable and the y for the term dependent variable. But obviously, when we apply functions to physics, x and y can be replaced with any other two variables. Okay, so for example, we could have velocity as a function of time. So in this is velocity or speed, whichever we are taking, as a function of time.
Hello, sir.
Yes.
So what do we actually mean by dependent and independent variables?
Okay, so I just explained that the term independent and dependent means that we can select the value of x without any dependence on y. Whereas because we have defined y as some kind of rule related to x or some kind of function related to x, that means the moment the value of x is selected, the value of y becomes dependent on that. So as you can see in this example, I have taken the value of x as 0, independent of anything else. But when I take the value of x as 0, the value of y becomes dependent on that. It becomes 3. When I take the value of x as 1, again I'm taking that independently. But the selection of x means that y becomes dependent on that. So y's value becomes 6. Is it clear now?
Yes, sir.
Okay. So here, for example, t would be the independent variable. And b would become the dependent variable. So an example, a simple example of a function would be, let's say y is equal to x square. Okay, this is an example of a function. So here X is independent variable. Okay. Y is dependent variable. And the function is defined in such a way that this fx is given by the formula x square. So that means that when I take the value of x as 0 this time, y's value is 0. If I take the value of x as 1, y's value is 1. If I take the value of x as minus 1, y's value is again 1. If I take the value of x as 2, y's value is 4, and so on and so forth. So it gives me the relationship between two variables, okay, between two variables through a particular mathematical equation or a maths expression, and it links what we call the independent variable with the dependent variable.
So why
Is this
is the
clear?
value of y related to x?
Sorry, come again, beta.
Why isn't the value of y related to x? I mean, if the value of y changes, the x also changes.
No, it is not that. That's part of the definition. What we write on the left hand side is the dependent variable, and what we write on the right hand side is the independent variable. Okay,
Sir, if we
so we
have
do
the
not take
value,
the value.
sir,
We
if
do
we have
not
the value of
just
y,
let me finish. Let me finish. Okay, so we do not take the value of x according to the value of y. No, we select the value of x independently, and according to the value of x, y becomes defined. Okay, that is the definition of a function. Yes, please ask your question.
yes, sir. Sir, what if we have the value of y in a function? Then what is the independent? What is the dependent?
It's not that way, beta. See, the definition of the function is when we write it in this expression, that y is defined as some kind of expression with respect to x. Then automatically, whatever is on the left hand side, that is our dependent variable, and whatever on the right hand side, that is our independent variable.
Okay.
There's a convention that we follow in the maths principle. So obviously, in a maths equation, if I give you the value of y, you can calculate the value of x from this also. But that doesn't mean that y has become independent and x has become independent. It just means that it's giving you the value of the dependent variable, and from that we can back calculate what is the independent variable. So for example, here in the last one that I have written, y is equal to x square. If I give you that, okay, y's value is 4, calculate the possible value of x. So you see there are two possible values of x. There is plus 2 and minus 2. But that doesn't mean that y has become independent and x has become dependent, because we have still written the function in this form, that y is equal to x square. Okay, so y is the dependent variable and x is the independent variable. You understanding the point?
Yes.
Okay, so this is the notation. Okay, in my definition, this is the notation, that whichever variable is written on the left hand side, that one is the dependent one, and whatever expression is written of a other variable on the right hand side, so that other variable becomes the independent one. So you can make a short note of this if you like. Okay, this is the definition of a function as far as calculus goes, or as far as maths goes. Okay, now when we're looking at the definition of a function, there is one important rule that we have to understand. A function is a relationship y is equal to fx such that any particular value of x okay must define a single or unique value of y. Okay, so for example, y is equal to square root of x, this relation, it qualifies as a function. It qualifies as a function because any value of x, of course, it has to be non-negative, defines a single or unique value of y. For example, x equal to 0 defines y is equal to 0. X equal to 4 defines y is equal to 2. Okay. But if I take an example like this now, that y is equal to plus minus root x. Okay. Now this is not a function because a single value of x.
Sir, for any root value, we have to consider only positive value, right?
Yes, root x is defined that way. No? I'll just explain the difference a little bit more in detail in a moment. Okay, but here you can see because a single value of x defines two values of y, okay, in general. So for example, if I take x equal to 1, I get y equal to plus minus 1. So this is not a function. Okay. This is not a function. Whereas this is a function. Okay. So for example, this equation actually is coming from the equation y square is equal to x. If I define, so this is also a relation. It's a relationship between two variables, but it gives us a solution of this because next step I would solve this is that y square minus x is equal to 0. Next step I would factorize this and solve this as y minus root x into y plus root x is equal to 0. So that would give me y is equal to plus minus root x. Okay. So there's a difference between saying, for example, that x square is equal to 4. This relationship gives me x's value as plus minus 2, and saying that x is equal to root 4. This gives me a unique value of x, which is just 2. Okay. These are just some of the general principles of algebra and mathematics. Okay. This nothing new for us really. Okay. But I'm just pointing this thing out. So when we are defining a function, we have to be aware of this thing, that we can only define that type of relationship which gives you a unique value of y for any particular value of x. If the relationship is such that it is giving you multiple or non-unique value of y for a particular value of x, that means it is not a function. It's a relation, but it's not a function. Okay, so hope this point is clear to all of you.
Sir,
Yes.
y square is equal to x will be a function.
No, y square is equal to x will not be a function, because you can see that the solution of y square is equal to x is giving us this kind of relationship between x and y, that y is equal to plus minus of root x. So this is not a function, because for a particular value of x is giving us multiple values of y.
Okay, got it.
Got it, no? Okay, but the same, but interesting thing is, now, if this expression was written like this, that x is equal to y square. So here I'm taking y as the independent variable and x as the dependent variable, because x is on the left hand side. Now this is defining a function. Okay, this is a function. This is x is equal to a function of y. So this is very much a function where y is the independent variable. So I can always change the name. That's not a problem of the variables. Okay. Though conventionally what we take x as the independent variable and x should be on the right hand side, and y should be the dependent variable and it should be on the left hand side.
Sir, could you show the above? We have to write
Sorry,
that above part, the function's definition and
you want me to scroll up? Okay, just a minute.
yes, sir.
Anshul, to answer your question, a quadratic equation is not the same thing as a quadratic function. Okay, a quadratic equation is the type when we take ax square plus bx plus c is equal to 0. So this has two roots. Okay, it has two roots equal to alpha beta. That's a separate matter. But a quadratic function is when we write y equal to ax square plus bx plus c. So in this function, what happens is when I take any particular value of x, it gives me a unique value of y. It does not give me two values of y.
Okay, sir.
Okay.
Yes, sir.
There might be two values of x that give a common value of y. That happens in y is equal to x square also. Whether I take x as +2 or -2, I'll get the value of y as 4. But that doesn't matter. The important thing is when I take a particular value of x, I'm not getting multiple values of y. I'm getting a unique value of y.
Yes,
So
sir.
that is the rule for a function, that for a particular value of x, we must get a unique definition or a unique value of y. Yes, Perf, you have some question, beta?
Yes, sir. So if when a linear equation would be a perfect square, so can we define that as a function?
Linear equation is a
Perfect square.
perfect, as in, like, explain to me how that
Like
works.
it has perfect roots, like a plus b plus multiplied by a plus b, we get the two roots.
No, but a linear equation is of this type now. A linear equation has only single term, not square term. So a linear equation would be this type: y is equal to mx plus c. You understanding, beta?
A quadratic equation.
Okay, so suppose I have this. Okay, so now y is equal to ax square plus bx plus c. Now this is a perfect square, so it becomes a into x plus something, let's say x plus alpha whole square. So there's no problem with that. That's still a function, because for a particular value of x, I'm getting a particular value of y.
Yeah, so that was the question. Like
Yeah.
if it's a perfect square, so it will give function.
But yeah, if you think of this like a quadratic equation, then you would have to equate y with 0. And that would show you that when y is equal to 0, you are getting a unique value of x instead of getting two values of x. So as a quadratic equation where y is equal to 0 instead, this would have one root, whereas a general quadratic term would have up to two roots. Okay, but that doesn't really affect the definition of the function over here, because the function is relating a new variable y with a quadratic expression of x. Okay, but this point is clear.
Yes.
Okay, so there's a difference between a quadratic equation and a quadratic function, right?
So how many answers will a quadratic function will give?
How many answers? What do you mean by how many answers, beta?
Roots. What do you call this?
A function does not have roots. Now, वही तो मैं समझाने की कोशिश कर रहा हूँ that a function. See, what is the meaning of roots of an equation? The roots of an equation means that some particular relationship in x should be equal to 0. This is satisfied by which values of x? That is the root of an equation. But here we are not defining an equation. Here we are defining a function that y is equal to some formula of x. So that means whatever value of x we select, we'll get a dependent value of y. So x can be the set of whole real numbers. So every real number of x will give us some particular real number output for y. X can be the set of only positive real numbers or non-negative real numbers, like when I take the function y is equal to square root x. So again, each value of x will give us a unique value of y.
So can we say that it has infinite solutions?
It has infinite
Solutions.
See, again, the term solution is wrong over here, beta. No, you should say values. No, so
Okay.
x has infinite number of values, because obviously x, we are talking about real numbers. So even if we take just two consecutive integers like 1 and 2, as you know, there are infinite real numbers between 1 and 2, right?
Yes, sir.
So there will be infinite values of y also for those corresponding infinite values of x. But see, there is matlab, it's not an equation to be solved. You're understanding my point? It is a
Yes.
relationship between two variables. No, so
Okay,
we don't have to think in terms of, you got my point now?
Yes, sir.
Yeah.
Sir, please
Sorry,
scroll up.
scroll up. You haven't finished. Okay. No, I'll be sending you the notes, so you can just jot down in short these points. Okay. I'll be sending you the full notes of this. You can jot down
Okay.
these points in short. Okay. So that, yeah.
Done. Sir.
Done, no? Okay. Okay. So having understood what a function is, this is just one key property of a function that we have to remember, that a function is a relationship such that any particular value of x must define a single or unique value of y. Okay, so that is why in the examples I've given you, this qualifies as a function, but this does not qualify as a function because it's giving me more than one value of x, sorry, more than one value of y for a particular value of x. There can be many different types of functions. Okay. It need not be just polynomials. Okay. So, for example, when we write a function like this, as I was telling you earlier, this is called a general polynomial function. So this is a okay. More specifically, if for example I have just up to the cubic term, cubic is maximum, then this is called a cubic function. Okay. Quadratic function you already know. Then I can have something like this, that y is equal to sine x, or y is equal to cos square x plus sine x. Okay. Or I can have y is equal to tan x plus 1, anything like this, anything where I'm operating the trigonometric relation, okay, on the variable x, on the independent variable x. So these are all examples of what we call trigonometric functions. So these are some of the things we'll be studying as we go along. Polynomials functions are in the category of what we call algebraic functions. And cubic function is a special case of the polynomial function. It is a polynomial function with what we say degree 3. Degree is the maximum power of x. So this one, it has of degree n, basically. Like that. Do any of you know what this symbol means?
Log. Natural log. To the base.
It's log, but specific type of log, right? Have you heard of natural log?
Natural log. Yes.
No, sir.
Okay, so if I haven't heard,
No,
no
sir.
problem. Okay. Okay, so to answer your question, root 4 is defined as 2. That's a definition in maths. Okay. If I say a is equal to root 4, by definition that is 2. It is not plus minus 2. Whereas if I say a square is equal to 4, then this relationship means that A is equal to plus minus 2, because this is solved as A square minus 4 is equal to 0, which
So then
means,
we cannot solve and prove that a is equal to root 4 is equal to only 2.
sorry, come again, Beta.
So we cannot solve and prove that again a is equal to root 4 is equal to 2.
No, it is a definition in maths, Beta, because I've not written the minus sign here. No? So square root of 4 is just 2. Square root of 4 is not minus 2 or plus 2.
Okay, sir.
It is just 2. Whereas if I wrote the expression like this, that a square is equal to 4, then when we solve it properly, it should give us this relation, that a minus 2 or a plus 2 is equal to 0. The product of these two things is 0. So that means either a can be 2 or a can be minus 2. So this expression,
sir.
that's why it implies that a is equal to plus minus 2. But this expression simply implies that a is equal to 2. Okay, understood now?
Sir.
Okay. Yeah, so this is a term we will learn very soon, but I'm just giving you some examples of different type of functions. This is called natural log. Okay. And this is in general called a logarithmic function. Okay. So these are some of the common types of functions. Out of this, the algebraic functions are the most common. Another common example is, for example, the function y is equal to 1 by x. Okay, so this is an example of an algebraic function, and it is called the, if you know the word already, it's called the hyperbolic function. Okay, don't get confused or psyched by the big terms that we are using. These are things that you will get used to as we learn more about mathematics and physics. Okay, so it's again an example of a algebraic function. This also comes in the broader category of algebraic functions. Okay, so as we learn applications of functions in physics, systematically we'll look at the different types of functions also. But our purpose here right now is not, to learn a big deal about functions. Okay, it is more about to learn the general definition of function, and then from that to come to the concept of rate of change of function. Okay, because that is where the story of calculus will start for us. Rate of change of a function. Okay. Okay. So now the other thing is, let's understand what is a graph of a function. So you can say a graph is a geometrical way of representing a function. Okay. So for any given function, y is equal to fx. Okay. A graph is what we call a geometrical way to understand it, or a geometrical representation of the relationship between y, which is the dependent variable, and x, which is the independent variable. So how we understand this relationship geometrically, what we do is we plot a two-dimensional axis system, okay, like this and like this. Okay. Now the convention is always the horizontal axis is taken as the independent variable, and the vertical axis is taken as the dependent variable. Now again, you can say why I cannot take the reverse, why I can't take the horizontal as dependent and vertical as independent. Well, I will say that it's a convention at one stage, but later when we do operations related to a function, you will see why that convention makes sense. Okay, so always the convention is that the horizontal axis should be the independent variable. Okay, the vertical axis should be the dependent variable. So for example, in a physics application, if you have defined, let's say, displacement as a function of time, then when I draw the graph, my time should be on the horizontal axis and displacement should be on the vertical axis, and not vice versa. But on the other hand, if I have defined velocity as a function of displacement, So now displacement is the independent variable because it's on the right hand side, and velocity is the independent variable because it's on the left hand side. So velocity will come on the vertical axis, displacement will come on the horizontal axis. Okay. So this is just a convention we follow. Now, once we have drawn our axis, next thing what we do is using the function, okay, we take convenient values of x and calculate y, okay, and write a set of what we call ordered pairs. Okay, let's say x1 y1, x2 y2, x3 y3, and so on and so forth. So just like you plot a graph in in your practicals or anything like that, okay, where obviously y1 is equal to f of x1, okay, and like this here yn is equal to f of xn. So once we have calculated this set of ordered pairs, next thing we plot these on the xy plane. So let's say when I plot these, I get these all points. I get various points like this. Okay. And next is we join them with a smooth curve. Okay. So when we join them with a smooth curve, we might get something like this. Okay. So this curve now represents the graph of the given function. So it gives us a visual representation that as I'm taking different values of x, how the corresponding values of y are changing. Okay. As you can see, I can have a situation where I have two values of x pointing to the same value of y. Okay. But I cannot have a situation like this, where a single value of x points to multiple values of y. If the graph of my relationship looks like this, then this will not represent a function, because single value of x is giving me two values of y here or multiple values of y here. So this is not a function. It's still a relationship, but it's not a function. So when we look at the graph of a function also, that graph should show one thing evidently, that for a particular value of x, I should not get multiple values of y. Okay. So this is the general procedure of drawing the graph of a function. Suppose we are given any function like y is equal to some quadratic function or some linear function or whatever. This is the most convenient way of drawing the graph, that we would take convenient set of values of x like x1, x2, x3 up to xn. We correspondingly find the values of y using the relationship of the function, and then we plot those ordered pairs as points on the xy plane, and then we join those points with the smoothest possible curve. So this is like a practical way of drawing the graph. Okay. Of course, it's dependent on our own talent of drawing a smooth curve also. So you can't say it's 100% accurate. If I want to make this 100% accurate, I would actually have to plot infinite number of points so that I don't have to draw a curve. They are naturally joining into a curve. So that can be done, for example, using a computer program, where instead of plotting a fixed number of points, I'm plotting literally infinite number of points by getting the program to plot ordered pairs for an infinite loop. But yes, in general, we can say the more the number of points we'll be plotting, the more accurate our graph will be. So if we are drawing a graph by hand, there's a trade-off. Right? If we want more accuracy, we have to plot more number of points. But the more the number of points we are plotting, the more time it's going to take. So
So can you copy this?
sorry, Beta, what was the question?
Can we copy this?
Sorry, I cannot hear you better. Can you speak louder?
How is it possible that y has two values of x?
Oh, I'll give you an example. Okay, if I'm plotting this relationship, that suppose I have this, that y square is equal to x. Now this is also a relation. No? It may not be a function, but it's a relation. Now we can always plot this relation. So we plot this relation. Now, for example, take the value of x as 1. You'll get the corresponding value of y as +1 and -1. So these 2 points will come in. Take the value of x as, let's say, 4. The corresponding values of y will be +2 and -2. Okay. And like this, if we plot the graph, we will get this kind of a graph. So this is giving you multiple values of y, or in this case, 2 values of y for a single value of x. So similarly, if I were to plot y square, or if I were to plot, y square is equal to x minus 2, for example, then this graph would become like this. Right? Instead of being here, it would tend to go up like this, So it's always possible to write an expression. Okay. Or for example, you have the equation of a circle. So y square is equal to, let's say, 4 square minus x square. So when we plot this on the graph, it will give us a circle like this of radius 4 and center at the origin. But again, does this represent a function? No, it does not represent a function. Yes, Rashmika, I'm coming to you. Okay, so this is not a function. Okay, this is not a function. Yes, Rashmika, what is your question, beta?
So how do we figure out the shape of the curve or the direction of the curve just looking at the equation?
Just looking at the equation, we cannot be done. So that's the thing. No? It's a painstaking process. We have to plot these points. Okay. And then from those points only, we understand the pattern of the graph, how it looks.
Okay, sir.
You understand? But
Yes,
for
sir.
us, what will happen? No? Like certain types of functions will be very common for us in physics. For example, quadratic functions will be common. So we will develop some techniques where by just looking at the quadratic functions coefficients A, B, and C, we'll be able to sort of guess that, okay, this is how that particular graph should look. In fact, if you know a quadratic functions graph, it has a particular name. No? It has a special name. It's called a parabola.
Yes, sir.
So we will develop techniques using calculus itself, that given any quadratic function, we can sort of guess even without plotting all these points that how that parabola should be looking. Should it be pointing upwards? Should it be pointing downwards? Okay, should it be cutting the x-axis, or should it be just touching the x-axis? All these things we'll be able to tell very fast by using the techniques of calculus. In fact, that is one of the purposes of calculus, no? Because it helps us analyze functions, not just in terms of rate of change, but also in terms of general properties of the function.
Okay, sir, got it.
Sir, how this graph helps us?
How does the graph help? Graph gives us a visual representation. Okay, so it helps us interpret what the function is like. Now, so for example, we are looking at, let's say, velocity as a function of time. The graph will tell us a lot of information. By looking at the graph, we can tell, for example, information about the acceleration. At which point of time it is accelerating, at which point of time it's decelerating, because where it's having a positive slope, where it's having a negative slope, etc. So, the more analysis of a function we can do, the easier it is to understand the relationship between the two quantities in the function. No? So graph is like an analysis of a function. You understanding the point?
Yes, sir.
Sir, doubt.
Yes.
Sir, for example, in the case of y square is equals to x minus 2. Sir, if we take the value of x as negative, then the value of y will not be defined. No, so how the graph
Yes, it will not be
plotted?
defined. Yes, that's true.
So in that case, the x has to be positive.
Yes, yes. So for example, if we have this relation that y square is equal to x minus 2. So this is only, so y is a real number. Only when x minus 2 is greater than equal to 0. That means x should be greater than equal to 2. So for this particular, so first of all, this is not a function. Okay, this is a relation only. This is a relation such that y is defined only for values of x greater than equal to 2. But for example, if I wrote this like this, that y is equal to square root of x minus 2. Now this is actually a function. This is a function. Okay, and again, this function is such that y is defined, or what I mean by y is defined, that y has real values only for x greater than equal to 2. So when we plot the graph of this later, we'll see that the graph also reflects this. The graph of this function will look something like this. This is 2. The graph of this function will look something like this. For x equal to 3, the value of y will become 1. For x equal to 4, the value of y will become root 2, which is 1.41. Like that, the graph will progress. But for example, if I plot the graph of this one, it's slightly different. It will show that it's not a function because it will give you plus minus values. Graph of this one will look like this. So at 3, it will give you two values of y, plus 1 and minus 1. So we can still plot a graph, okay, but that graph does not represent a function. That graph just represents a general relationship. Okay.
Excuse me, sir.
Yes.
So what is the difference between a relationship and function?
See, it's like relationship is a superset. Function is a subset of relationships. Okay, so in fact, you can say that, see, relationship is anything in maths. Like I can define a relationship between more than two variables also. I can say that z is equal to x square plus y square plus 3. This is also relationship, but it's a relationship between x, y, and z. I can say z square is equal to x square plus y plus, let's say, 2x or whatever. This is also a relationship between x, y, and z. But a function is a specific type of relationship. A function is a relationship that, first of all, it links a dependent variable with an independent variable, and secondly, it links it in such a way that for every value of x, that is the independent variable, we get the unique value of y. Okay, you understanding the point?
Yes, sir, got it.
So every relationship is not a function, because function is subset of relationships, but obviously every function is a relationship. Okay, so it's a specific type of relationship, you can say, that does what we have defined it as. Okay. All right, so now that we have understood, like
so how can we define relation?
Relation is what the term relation means. It is a connection between two things. It's called a relation between two or more things. Okay.
So while plotting a graph, since we cannot plot infinite points, how many points ideally should we locate?
See, that is a subjective matter. That depends on how accurate we want the graph to be. You know, how many points. So here, you know, our purpose is not going to be to plot more and more accurate graphs. Okay. For that, there are programs written and all that, you know, so we don't need to get into that. Our purpose here for drawing graphs now is just to understand the you can say understand the properties of a function. So in fact, we are not going to get into graphs by plotting points. Actually, we are going to get into graphs by the method of calculus later. Okay. There are only certain general types of graphs that we'll be studying for physics, and for that we will not be drawing those graphs by plotting points in future. We will be drawing those graphs actually by using the techniques of calculus. The purpose of the graph is going to be just to understand the properties of the function. Okay. So you don't really need to worry about how to plot a graph using points. That is just a general method I've told you. Here, our purpose is going to be more analysis of the function using calculus. So plotting the graph using ordered pairs is just a method I've given you, but we will not be solving any questions using that particular method. Okay. Now, having said that, let's look at some very common types of graphs, okay, and some techniques for plotting them, okay. So common examples of graphs. So the first is what we call a linear function. That is a polynomial of degree 1. So we can say that is y is equal to mx plus c type. Or you can write it as ax plus b also, where m and c are constants. So in general, you know what the graph of this type of function looks like. It looks like a straight line, where m is the slope and c is the y-intercept. So I'll just draw some examples. So for example, if we have a straight line that looks like this. So this is an example where the y-intercept is positive, okay, and the slope is positive. So this will be one where m is greater than 0 and c is also greater than 0. Okay. Similarly, if I have a graph like this one, now you can see here that the y-intercept is positive, but this angle is obtuse angle, or the slope is negative, because as x is increasing, the value of y is decreasing. You can see. So you can see m is negative because y2 minus y1 upon x2 minus x1 is a negative quantity. Whereas here, if you see, y2 minus y1 upon x2 minus x1 is positive, because as x is increasing, y is also increasing. It's positive. Okay. Similarly, we can also have a graph where the y-intercept is negative, but the slope is positive. So that would be a graph that looks something like this. We just bring this line down over here. So it still has a positive slope, but the y-intercept is negative now, because this point, as you can see, is a negative point. And similarly, a line over here, this would have m negative and y-intercept also negative. So these are the various types of straight lines. Okay. Now we'll come to more about straight lines once we understand rate of change in detail also. So this is the first common type of example of graph. Then the second example of graph which we will be looking at is the basic quadratic function y equal to x square. Okay. Later we will come to the more general one also, y equal to ax square plus bx plus c. Okay. But here we'll just start with the understanding of the most basic quadratic function, which is y is equal to x square. So this one, as I'm sure all of you already know, this graph looks like this. As you can see, I'm not very bothered about plotting exact graphs. Okay. Otherwise, I would have used a software. Okay. I'm more concerned with understanding the pattern of the graphs theoretically. So +1 and -1, if your value of y is 1. +2 and -2, the value of y jumps to 4. And so on and so forth. Now later we will see that for this type of function, the graph can be like this, it can be like this, it can be like this. All these different types of parabolas are possible. So in general, this shape is called a parabola. A parabola is the geometrical name for the shape of a quadratic functions graph.
Sir, can you explain the linear function graph again?
Linear function is the graph of a straight line. So any straight line graph, it has two important properties: slope, which is the coefficient of x, and y-intercept, which is the independent term. Okay. So how we understand slope is, if you have any given linear function y is equal to mx plus c, and it is passing through 2 points, okay, x1 y1 and x2 y2. So both these points satisfy the equation of the line. So you have y2 is equal to mx2 plus c, and you have y1 is equal to mx1 plus c. So if you subtract these two, you get that relation that y2 minus y1 is equal to m times x2 minus x1. So this m, which we call the slope of the straight line, is equal to nothing but the rate of change. It is y2 minus y1 upon x2 minus x1. So if the line looks like the first two graphs that I've drawn, like this one, you can see that the rate of change is positive, because when x is increasing, y is also increasing. So the ratio of y2 minus y1 upon x2 minus x1 will be a positive quantity. So that will happen in which situation? When m is positive. So that's why I put m as positive over here, or m as positive over here. Whereas on the other hand, if y2 minus y1 upon x2 minus x1 is negative, that means the line should look like this, because y should decrease as x is increasing. The rate of change should be negative. Okay. And similarly, what is c? If you put x equal to 0, the corresponding value of y that you get is c. So this is called the y-intercept. Okay. So this is something pretty basic that you would have learned in maths, right? In coordinate geometry of maths. Okay. The equation of a straight line, y is equal to mx plus c. Okay. And the significance of m, which is the slope, and the significance of c, which is the y-intercept. Is it clear now?
Got it, sir. Yes, sir.
Yes, Parv?
Sir, so the number of values of the independent variable can be more than one for a single dependent variable.
Yes, yes, yes. Like you can see in the quadratic function, I'm getting the value of y for two values of x, no? minus 2 and plus 2. So there's no problem with that. But for a particular value of x, I should not get multiple values of y.
Okay, sir.
Okay. Another common graph, okay, albeit we're not going to use it so much in physics immediately, at least, is the basic cubic one. Y is equal to x cube. Okay. So this has this sort of a nature. Starts from 0 for non-negative values, okay, and it rises very rapidly. And similarly, on the negative side, it drops very rapidly. So this negative side is like an inverted mirror image of this. Okay, because as you can see, for the values, 1 will give you 1, but minus 1 will give you minus 1. Then 2 will jump to 8. So minus 2 will have dropped very rapidly to minus 8. And from there, it drops even at a more alarming rate. Okay. So my graph is not drawn exactly to scale. If I had drawn it exactly to scale, it would have been a little different. Like that.
So
If I
this
had drawn it
cannot be exactly mirror image, because here the values are greater.
It is exactly a mirror image. See, if I had taken this now and drawn a mirror image over here and then inverted that mirror image here, then that's the values you're getting. You understand me? Minus of a whole cube is exactly minus of a cube. No? So if I take any a over here, I'm getting a value of a cube over here. So if I take minus of that one over here, I'll get exactly the same distance on the negative y-axis. Okay, so it is an inverted mirror image. You understanding now?
Sir, understood.
Okay. So this is the basic cubic graph. But later using calculus, we will also be able to plot more general cubic functions like ax cube plus bx square plus cx plus d. Okay, which will have a more complicated graph compared to this, depending on the values of a, b, and c, and d, of course. Okay, so we will see that right now, given some general cubic graph like this, it might be very time taking and painstaking for us to plot the graph. But one of the things that calculus will help us to do, apart from understand the rate of change, will also be to plot these kind of graphs.
So don't we have a name for this graph like parabola?
Yeah, unfortunately, we don't have. And parabola is a specific name, but in maths, the cubic graph does not have a specific name.
Okay, sir.
So the graph, the
Yes,
shape
tell
of
me,
the
madam.
graph will change as the function change, in quadratic, in cubic function.
Sorry, come again, Anshul.
So the shape of the graph will change as the function change in.
Yes, absolutely. No? Every function has its particular type of graph. No? Like x square has a particular type of graph, x cube has a different graph, linear function has a different type of graph, right?
Yes, sir.
Another example of graph is the hyperbolic function, y is equal to 1 by x. Okay. This is called the hyperbolic function. So this one has another interesting graph. So first of all, here you can see that for x equal to 0, y cannot be defined. Division by 0 is an illegal operation in maths. No? But if x is very small but positive, like suppose x is equal to 0.0000, okay, that is 10 raised power minus 20, let's say, then y becomes how much? It becomes 10 raised power 20. So it becomes a huge number. Okay. Whereas if x is a negative number of this type, minus of 10 raised power 20, then y becomes a huge negative number. If x is a very small negative number, then y becomes a very large negative number. So that's why the graph looks like this over here. The closer the value of x is to 0 on the positive side, the closer y is to plus infinity. And it decreases like this. And as x goes to infinity, y's value tends to 0. And this side looks like a mirror image of that. Again, a inverted mirror image.
Sir, isn't this similar to the graph of tan x?
Yes, tan x also has this thing of these in maths you might have read, these are called asymptotes. These kind of lines are called asymptotes. So in trigonometry recently you might have seen the graph of tan x. Okay, so how that one looks, that looks like this. At pi by 2 and minus pi by 2. But then it continues also, no? That graph. Have you seen this graph in trigonometry yet in maths?
Yes.
So there are like so many different types of graphs now, which can be very interesting also. Thing is, we should treat them as interesting and not as complicated. There's no need to overburden ourselves. Okay. This is an example of a trigonometric graph. Similarly, have you seen the graph of cosec x and sec x?
No,
So
sir.
they are also okay. So you will see in maths. Don't worry. They are also interesting graphs. Okay. All right. So this is just to give you an idea that what some of the basic shapes and graphs look like. Okay. Our purpose in physics is not going to be so much about graph plotting. It is more going to be about rate of change. So that is what we are coming to next. So rate of change of a function. And through this, we will see that the first type of operation in calculus called differential calculus will start for us. So for any given function, y is equal to fx, if we define two types of rate of change. One is the average rate of change. So just like we had seen average speed, average rate of change is denoted by the symbol delta y by delta x, or y2 minus y1 divided by x2 minus x1. This is the formula, and this is the definition of average rate of change. So as you can see, average rate of change is defined for an interval in x equal to x1 to x equal to x2. So our delta x is x2 minus x1. Okay, so before you note down this definition, now let's see the graphical meaning of average rate of change. So let's say I'm taking some kind of function by imagination, that this particular function, without writing its expression and all that, let me just assume that its graph is something like this. Suppose the graph of this function is like this, and I want to calculate the the average rate of change between the points x1, which is over here, let's say, and the points x2 over here, which is like this. So how we'll interpret this definition now? Okay. This definition, how we'll interpret it? So at the point x1, I'll draw the vertical line, and that will show me the point on the graph which has the x coordinate x1, and its y coordinate becomes y1. And similarly at the point x2, I'll get some corresponding value of y2. Okay. So now look at this equation that I'm trying to solve, that the average rate of change between x1 and x2 is y2 minus y1 upon x2 minus x1. So you can see in this graph that this over here is x2 minus x1, this distance. Okay. And you can see that this distance over here is y2 minus y1. So if I just extend this line here, you can see that this is delta y, and this is delta x, which is equal to x2 minus x1. So that means if I were to join these 2 points with a straight line, what is the relationship of this y2 minus y1 upon x2 minus x1 with that particular straight line? It would be the slope of that line, because that's how we define slope of a straight line, right? So that means what is geometrically, what is the meaning of average rate of change? It is the slope of this type of straight line. And this type of straight line is given a specific name. It is called a secant line. Okay, you might not have heard this term before. It is called a secant line. So the geometrical interpretation of average rate of change is that it is the slope of the secant line. And what is a secant line? It is a line that specifically joins the 2 points x1 and x2 on the graph. Is the straight line that joins two specific points on the graph at x equal to x1 and x equal to x2. Okay, so just review this definition of average rate of change once. Okay, jot down any important points you want to, including the graph. Then we'll look at a couple of examples, and with those examples it will become very clear that average rate of change is something very simple, okay, both in terms of graph as well as in terms
So we
of
can
formula.
say that this slope between delta x and delta y is the average rate of change.
Yeah, average rate of change is this ratio only, na? Delta y divided by delta x. So in terms of geometry, that ratio of delta y by delta x is becoming what? Is becoming tan theta for the straight line.
Yes,
is the slope.
Yes, sir.
So
Yes.
So can we say that this is the general formula we write it, and in the previous lecture, the ST graph was the example of this?
Yes, very correct. And this is the general expression for average rate of change. And in the previous lecture, we had seen the application of this applied to motion kinematics, that if the graph is S versus T instead of a general Y versus X, then the average rate of change will represent what? The average speed, because the average distance with respect to time is defined as the average speed. That's correct. No? But similarly, if it's a velocity time graph instead of a distance time graph, then the average rate of change will represent what? Average acceleration, because it will be change in velocity upon change in time.
Yes, sir.
Okay, so let's work out a quick little question here. So y is given to us as
Sir,
yes.
so how this is a function, because y2 is cutting at 2 points, no?
See, once again I'll repeat that there is no problem with a graph like this. It is giving you the same value of y at two different values of x, 2 or 3, it doesn't matter. But at a particular value of x now is giving you a unique value of y. At any value of x, you can see there's only one single value of y, no?
Yes, sir.
Okay. So this is a function. The problem is when the graph is like this. If the graph had been like this, then there's a problem, because at a particular value of x, it's giving you multiple values of y.
Okay, sir.
That is not allowed. No? So that's one easy trick to understand, no? Which one is a function, which is not. Draw a vertical line. It should not cut the graph at multiple points. Okay,
Okay, sir.
Yeah. Okay. Now for this function, x cube plus 2x. Okay. Find the average rate of change of y with respect to x for the interval x equal to 0 to 1 and for the interval x equal to 1 to 2. Okay, just try this question out and send me the answers on the message quickly. Yeah, Harshit, I will come to the answer of that question when we discuss about instantaneous rate of change next. Now, you will get the answer to that question. Okay, so let's see. You got the answers. Yes, very good. Aryan, Shan, Pratyush, Anshul, Parv, Harsit, Maitreyi, all your answers are correct. Ishita, very good. Okay. So it's just formula based, as you can see. So we will find delta y by delta x by just using the formula. It is y2 minus y1 upon x2 minus x1. And further, y2 is basically what? The value of the function at x2. Y1 is the value of the function at x1. So we can write it like this. So in this case, what is the function? The function is x cube plus 2x. Okay, so for the first part, I'm taking x1 as 0. So y1 becomes the function's value at 0. So that is 0 cube plus 2 into 0, which is 0. And x2 I'm taking as 1. So y2 becomes the value of the function at 1, which is 1 cube plus 2 into 1. So that is 2. Okay. So now what is my delta y by delta x? Sorry, that is 3. My mistake.
1 upon 3.
That is y2 minus y1 divided by x2 minus x1. So it's equal to 3. So this becomes the answer for the first part. Now similarly for the second part, I'm taking x equal to 1 to 2. Okay. So that means I should take x1 as 1. So y1 is f of 1, which we already seen is 3. But I'm taking x2 this time as 2. So y2 will become f of 2. So that is 2 cube plus 2 into 2, x cube plus 2x. So that's becoming how much? 8 plus 4, 12. Okay. So this time my delta y by delta x will become y2 minus y1, which is 12 minus 3 divided by x2 minus x1, which is 2 minus 1. So it is becoming 9. So as you can see, there is nothing difficult about finding the average rate of change. All of you almost have got this correct. You have to just be careful not to make any calculation mistake. Rest, this is very easy. So now next, from average rate of change, we will move to the more complicated definition of instantaneous rate of change. And today, unlike in the previous class, we will use the calculus notation for this. So for a function y is equal to fx, we use a special symbol for instantaneous rate of change, and that is dy by dx. If you've been going through your module, you might have seen this symbol. This is read as instantaneous rate of change of y with respect to x. So this is defined as a change in y divided by a change in x, but under a very special condition, and that condition is now called a limit. So the limit or the condition is that the change in x should be very small, so small that it is tending to 0. This term, limit delta x tending to 0, this is to show that the value of delta x should be extremely small. Okay. Or there is a word for it, it is called infinitesimal. Infinitesimal can be thought about like 1 upon n, where n is tending to infinity. So if n tends to infinity, then 1 upon n tends to 0. So this concept, as you can understand, is a bit more abstract. There's no direct formula for it, like we have for average rate of change, y2 minus y1 upon x2 minus x1. But there is a good graphical interpretation of it, and we are coming to that next. We say tends to 0. If it is infinitesimal or extremely small, that means its value tends to 0. It's not equal to 0, but it tends to 0. Okay, so let's look at the graphical representation.
Can you scroll up for a second?
Yes,
okay, please.
Done, sir.
All right, done.
Yes, sir.
Okay. So graphical interpretation of instantaneous rate of change. Let's understand that. So let's say a particular function's graph is this particular curve now. And I want to calculate the instantaneous rate of change at this point x. So I want to find dy by dx, that is the instantaneous rate of change at the point x equal to x. Okay, it's not defined for an interval, it is defined for an instant. So what I'll have to do is I'll have to plot this particular point on the graph, which is this point, and then I'll have to, in principle, I'll have to zoom in as much as I can. So let's say I zoom in as close as I can over here, so that now I can plot another point which is extremely close to the first point. It's like the next consecutive point. So when I plot this second point, I can see that the change in x is infinitesimal. That's extremely small. It's tending to 0. So between this point and this point, the interval, now I'll call it dx. So dx is basically what? It is the value of delta x tending to 0. It's an infinitesimal interval. So the corresponding value of y over here would have been this, let's say, for x equal to x. But when I take the next consecutive point, the value of y also changes by a very small amount. So this change in y, this is now a differential change or a very small change. That is, it's a delta y tending to 0. So when I calculate the rate of change between these 2 points, given that I've tried to bring them as close to each other as possible, then I'm ultimately looking at joining them with a straight line. Okay, but again, for that straight line also I'm using a specific condition that those 2 points are almost merging to each other. Those 2 points should be almost merging to each other, because dx is the value of delta x when it is tending to 0. Okay, so when I use this definition that is tending to 0, you will see that we come to a condition where the 2 points that I've drawn, the red colored dot and the violet colored dot, they almost merged into one. Okay, so when that happens perfectly, if I've drawn it very accurately, then I can say that this is what we call a tangent line. So a perfect tangent would be one which is drawn between 2 points which are actually merged into each other. So in this graph, come back to it. So in this graph, you can see that dx, it is called a differential interval. So this is again a new term for us, differential change or differential interval. It's a differential change in x. dy is similarly a differential change in y. Okay. So it is equal to delta x under the limit that delta x is tending to 0. this is equal to delta y under the limit that delta y is tending to 0. So what happens is when we apply that concept over here, okay, we see that the 2 points are almost merged into each other. And that kind of a line is called the tangent line. So the graphical interpretation becomes that this is the slope of the tangent line drawn at x equal to x. This becomes the geometrical interpretation of instantaneous rate of change. So what is a tangent line? It is a line joining a given point on the graph to another point which is extremely close to it. So it almost merges with it.
Sir,
Yes.
so could you please explain one more time how differential change in x and y is tending to 0?
It's not how, that is the definition. Okay, differential change ka matlab hi ye hai that it is a change in x that is so small that it is tending to 0. So it's as small as you can imagine. So if I say dx is 10 raised by minus 50, this is also not a correct way of saying it. We can say it's approximately minus 10 raised by minus 50, because we could have a number like 10 raised by minus 60, which is even smaller. So it is the smallest possible that one can imagine. You're understanding the point? So it's a bit abstract. Okay, so it's like on the graph, that second point is coming so close to the first point that it is almost merging with the first point.
So like
in
if
that
x
case, what
is
is
equal
the
to 1,
change?
then x 2 will be 1.0001.
Yes, correct. Okay, so for example, if I take x equal to 1 and if I take dx equal to 10 raised power minus 20, let's say, then x plus dx will become 1.00, this going 19 times and then 1. Okay, but even then that is a finite value of dx. That is not an infinitesimal value. Infinitesimal value will be when dx is taken as 1 by n, where n tends to infinity. So you can imagine that. So there won't be a finite number of zeros here. There will be an infinite number of zeros and then that digit. So it's something that is just left to imagination. We cannot actually plot that point. So that is where this whole machinery of differential calculus will come in. That how we actually calculate the slope of the tangent. You are understanding the point? So this is the abstract geometrical representation. It does not give us a formula.
Sir?
Yes.
So this is a special case for tangent line, or every time the tangent line is a secant line which cuts the 2 consecutive points?
No, so that is the definition of tangent line, that it is not cutting 2 consecutive points, 2 points actually. It is cutting 1 point and joining it with the next point which is merging with it.
So
The
this
next
is a
point is
special case, or it happens every time?
This is the tangent line. This is how we define tangent at a point. Okay. If I want to draw the tangent at, let's say, this point now. So what I have to do is I have to take this point and another point so close to it that is almost merged with the first point, and then join those two with a straight line. So this will be the tangent line. Whereas if I want to draw the secant line, then I have to define 2 separate points, like this point over here and this point over here, and I have to join those 2 separate points with a straight line. So any point drawn between 2 distinct points, any line drawn between 2 distinct points, that one is a secant line. And any line drawn in such a way that it is joining 2 points which are so close that they are merged together, that is a tangent line. So they are the 2 different types of lines that we can define. So this is the general definition of the tangent line. It is a line joining a given point on the graph with another point which is almost merging with the first point. Okay, so what we understand here that the slope of tangent cannot be directly determined from the graph. There is no direct formula for it. Okay. Okay. So instead of that, it has to be calculated using a separate process or separate method, and that is called the method of differential calculus. And this is what we will be studying for the next couple of weeks. Okay, starting today, a little bit. Okay.
Sir.
Yes.
Could you please explain one more time instantaneous rate of change?
Instantaneous rate of change is defined over here. Okay, it is the change in y upon change in x for an interval of x, delta x, so small that it is tending to 0. So that type of an interval is called an infinitesimal interval because it tends to 0. Okay, so that is the definition of instantaneous rate of change. Like we talked about instantaneous speed last time, no? It is the distance divided by time, but for a very, very short interval of time. So now we are giving it a more specific definition that it is dy by dx, where dy is a value of delta y which is so small that it tends to 0. Dx is a value of delta x which is again so small that it tends to 0. Are you understanding now?
Okay, sir. Yeah.
Okay. So on the graph, what is dy and dx? You can see that if I were to draw a particular point x comma y on the graph, and then I magnify this graph as much as I can. Okay. So you can see that this red colored dot, it represents x comma y. Now the violet colored one represents another one which is very close to it, so small that when I zoom out, it almost merges with the first one. Okay, so then the difference in the x coordinate between these two is dx. The difference in the y coordinate between these two is dy. And the line joining these two will become what we call the tangent line. So geometrically, what is the definition of the instantaneous rate of change? It is nothing but the slope of the tangent line. Okay, is it clear now?
Yes, sir.
Okay, but as you can see, this is just an idea. There is no formula in it yet. So how we'll develop the formula? The formula is developed by a separate process dedicated for it, and that is called the process of differential calculus, or that is called the method of differential calculus. Okay. So next we come to differential calculus. So differential calculus will develop a method through an operator called differentiation. Okay. So differential calculus involves an operator which is given by this symbol. You can read it as d by dx, but the meaning of this symbol is it is something called differentiation with respect to x. Okay. So when this operator is applied to a function, what this operator does is it gives us the instantaneous rate of change of y with respect to x. So this is the symbol for the operator d by dx. And when we operate it on y, where y is some kind of function of x, the output that that operator gives is that it's the instantaneous rate of change. Now you can think of it like a box, okay, which does an operation. So it's an operator. Now, when we input the quantity y is equal to fx into that operator, what output it gives us? It gives us the output of dy by dx or differentiation of the function fx. And what is this actually? It is the rate of change. the instantaneous rate of change. It gives us the value which is the instantaneous rate of change. So this is a completely new, branch of mathematics which is applied in physics for us. Okay. And we have to systematically learn the principles of differentiation. Okay. So today, so far, we've just learned that what the operator does. We've not learned how it does it. We have learned what the operator does. It gives us, when we input the function fx into it, as the output of it, it gives us the instantaneous rate of change. Okay, so now let us understand some of the formulae that are used in differentiation. Sorry?
Scroll up for a second.
Yeah, sure.
Yes.
Okay. So let's look at, first of all, the basic formulae of differentiation. So differentiation of a constant is equal to 0. This is the most basic and most fundamental one. C is a constant. And the logic of this is very easy to understand. If y is equal to a constant, that means the function we are defining is actually a constant function. Then you can visualize how the graph of this function looks like. Now, what would be the graph of y versus x for a constant function?
Straight line.
Yeah, but what type of straight line?
Parallel to x-axis.
Very good. Parallel to x-axis. Now it will look like a horizontal straight line. So that being the case, now what is the slope of that sort of straight line?
Zero.
No? Zero. That's it. So the slope of, so the graph itself is a straight line, where if we draw the tangent at any point, it's that same straight line only. No? So it has a slope equal to 0. So the instantaneous rate of change. Okay, so whether we calculate dy by dx or we calculate delta y by delta x, it is equal to 0. Okay, slope of tangent, instantaneous rate of change, or slope of secant line, average rate of change, both will be 0 because it's nothing but a constant function. Okay. So this is the most basic type of formula for differentiation, that if our function is a constant function, then its instantaneous rate of change is 0. This is like, you can almost say it's like too simple to be defined also. Like if I say that, distance is constant, it's 20 meters, that means it's not moving at all. No? So what should be the instantaneous velocity? It should be 0. What should be the average velocity? It should be 0 because it's not changing with respect to time. So it's something very obvious. It's almost too obvious to define also. Okay. Now we come to the next one, linear function. Now this one is also pretty obvious. Linear function's graph is a straight line. So differentiation of a linear function will become the slope of that straight line. Okay. So whether we draw the tangent line at a particular point or we draw the secant line between 2 points, we can see that the slope is the same. So dy by dx will be the same thing as delta y by delta x will be equal to m. So slope of tangent drawn at any point is equal to the slope of secant line, which is equal to the slope of the line itself. Okay. So far you would have found it very easy. Okay. Now we come to the more tricky example. If I have the function y is equal to x square, then what should be dy by dx? Let's understand this. Okay. So we will understand
2x.
this by a 2x. Very good. Okay, but there's a process behind this which we had discussed last time indirectly. Okay. So what we want to do here, dy by dx or differentiation of the function x square. Okay, we want to actually find delta y by delta x under the limit that delta x is tending to 0. Right, this is what we want to do. Okay, so now remember what was delta y by delta x? It was equal to change in y. Okay, so that is f of x plus delta x minus fx divided by delta x. Okay, because we can take x1 as x and we can take x2 as x plus delta x. So y1 becomes f of x1, which is fx, and y2 becomes f of x2, which is f of x plus delta x. ऐसा होता है ना?
Yes.
So please repeat.
What is the definition of delta y by delta x? It is y2 minus y1 upon x2 minus x1.
Yes.
So just apply the definition over here. Got it now?
So that f of x plus delta x minus f of x, where it came from.
Exactly, that's what I've explained over here. No? If I'm taking my x1 as x, so what is my y1? If it's fx, right?
Yes.
And if I'm taking my x2 as x plus delta x, then what is y2? It is f of x plus delta x.
Okay, sir.
Understood? So this is coming from here only. Okay, this
Yes,
is your y2 minus y1 upon x2 minus x1. Now when I substitute this thing in the limit over here, see what it will become. So this is the definition of delta y by delta x for this. Okay, but now what I want to do on this, I want to apply the limit that delta x is tending to 0. Okay, so when I apply that limit, it will become dy by dx. Okay, so that will become limit delta x tending to 0, the change in y divided by the change in x. This should be delta x in the numerator just. Okay, so far clear? It's the same expression I've written, but I'm now applying the limit that delta x should be tending to 0. Okay, so let's apply this to the function now. Let's apply this to this function. So what is my function? My function is x square. So what will dy by dx become? It will become limit delta x tending to 0. Now what is the numerator here going to be? It is going to be x plus delta x whole square, because the function is x square, minus fx will be x square divided by delta x. Correct so far?
Yes, sir.
Okay, now expand this and just solve this algebraically a little. So this becomes x square plus 2x delta x plus delta x square minus x square divided by delta x. So further this becomes how much? This becomes limit delta x tending to 0 2x delta x plus delta x square divided by delta x. So next thing what we can do, we can take delta x common. So this is a very critical step I'm coming to next. When I take delta x common, in the numerator I'm left with 2x plus delta x. Okay, now pay attention here. The important thing is delta x is tending to 0, but delta x is not equal to 0. So if it's not equal to 0, it's legal to cancel these two. 0 by 0 is not defined, but anything non-zero divided by itself is 1. So we can cancel these two.
Yes, sir.
Right. So now I'm left with what? I'm left with this quantity that it is equal to this expression 2x plus delta x, but under the condition that delta x is extremely small, it is infinitesimal. So imagine delta x is like something like 10 raised to minus 50 or something. So it's so small compared to 2x that we can neglect it. Okay. So it's so small compared to this 2x term that delta x can be neglected. So its value will become how much? Its value will become 2x. So that is showing us that what is the value of dy by dx? Its value is equal to 2x. Okay. So I'll just minimize this for a moment and leave you with this to just go through the expression once and make sure how we came from this step over here right up to this step over here. We just use normal algebra, a plus b whole square formula.
Sir, in the second last or the last step, we consider delta x tending to 0 or negligible, and hence we got that dy upon dx is equal to 2x,
Is equal to
right?
2x. That's correct. Yes. Because see, up till the time when delta x was in the denominator, we cannot substitute it as 0 because division by 0 is a illegal operation in maths. But once we were able to resolve it in such a way that delta x is not there in the denominator anymore, now we can put delta x tending to 0.
So now this is like instantaneous rate of change
Yes.
of y with respect to x.
Yes. This is now the instantaneous rate of change for the function y is equal to x square. Okay, are you following this?
Yes, sir.
Okay. So this tells us that what is the rule that we have got from differentiation, the formula that we have got from differentiation, that differentiation of x square is given by 2x. If y is equal to x square, then instantaneous rate of change of y with respect to x will become 2x. Okay. So this is an additional formula that yes.
Sir, does it have any relation with the that power?
It does not. Now we'll see that pattern next. Okay. Just give me a couple of minutes. I'll show that next. Okay. Now, how would we, for example, if we had y is equal to x cube, how would we get this differentiation of x cube? Think of a similar method now.
Yes.
I would have to use this relation that the function is x cube. So differentiation of the function is defined as the limit delta x tending to 0, f of x plus delta x minus fx upon delta x. This is the basic definition, right? Now this has to be applied to this. So substitute this over here. So this will become limit delta x tending to 0, x plus delta x whole cube minus x cube upon delta x. ऐसा हो जाएगा? Right. Now expand this further. So x cube plus 3x squared delta x plus 3x delta x squared plus delta x cube. Okay, and then you have that last term minus x cube divided by delta x. So you can see that this is becoming limit delta x tending to 0. Now x cube cancels out. So I have 3x squared delta x plus 3x delta x square plus delta x cube, but the whole thing divided by delta x. Now you must have guessed again what we'll do. We'll cancel delta x with the numerator. So we'll be left with what? Limit delta x tending to 0, 3x square plus 3x into delta x plus delta x square. So now you can see that because delta x is tending to 0, we can neglect this term. This term tends to 0 and this term tends to 0. So what we are left with? We are left with just 3x square. So that is what my dy by dx is becoming. So here this becomes 3x square. So notice a pattern. Differentiation of x square was 2 into x. The differentiation of x cube is becoming 3 into x square. So the general formula that we get, the general formula is that differentiation of x to the power any n will become n into x to the power n minus 1. So you substitute n equal to 2, so you will get this. You substitute n equal to 3, you will get this. Like that, you substitute any value of n, and this formula gives us the differentiation of x to the power n with respect to x.
So, sir, we don't need to memorize the derivation, right?
No, you don't need to memorize the derivation, but you should understand the process of derivation. Okay.
But this is only for the function if y is equal to x raised to power n.
Yes, only for that type of function. If y is given by x to the power n.
So here x can be more than one term as well.
Yes, there can be more than one term also. Okay. And for that, we'll be using some properties.
Sir.
Yes.
Sir, does n have to be an integer here, or can it be a fraction or decimal?
So the interesting thing that n can be any real number. Okay. So the interesting thing about this formula is that we have seen above the examples where n are two particular natural numbers, 2 and 3, but n need not be a natural number or a whole number also. N can be any real number. Okay. And just like we have done the proof for n equal to 2 and 3, you can think of this like the proof. The proof of this formula for the specific value of n equal to 3 is this process. For the specific one, n equal to 2 is the earlier one. So like that, there is a general proof also, but we'll come to that later. Okay. So this can be any real number. Okay. So for example, differentiation of x to the power 5 will become 5x to the power 4. But similarly, you tell me yourself now, if y is equal to 1 by root x, then how I'll find dy by dx?
Sir, taking the power of root x is equal to half minus half.
Yes. So first thing I can do is I can express this as this in the denominator. Then I bring this to the numerator. Right? This is what you were saying, beta?
Yes, sir.
Okay. And now I'll just substitute the value of n as half. So differentiation of y with respect to x will become differentiation of x to the power minus half. So that is n x to the power n minus 1. So this will become how much? Minus half x to the power minus 3 by 2.
Yes, sir.
Okay, so that becomes my answer. So I can leave the answer this way also, or I can bring this to the denominator and write it this way also. Okay, or I can further expand it and write it this way also. Okay, any of these answers are okay because they are equivalent to each other.
How can we write 2x root x?
Sorry, how can we write?
Like minus 1 upon 2x, 3
x
upon
root x कैसे
3
लिखा?
by 2. हाँ ये
Okay,
last
see,
की
x to the power 3 by 2 को ना वैसे लिख सकते हैं 1 plus half. Correct?
हाँ.
So that is x to the power 1
x and root x.
Correct, है ना? So this is just the reverse process of this, that x to the x into root x can be written as x to the power 3 by 2. How we do this? So the reverse of this is this. Okay, people. So now using this, one more thing we can see is that if we want to differentiate, let's say 5x square. Okay. Now I know that the differentiation of x square we had just seen is how much? It's 2x.
Yeah.
Okay. So what about dy by dx here?
Sir, dy of dx by of 5 will be constant.
No, but it's multiplied, no? So ये 5 बाहर आ जाएगा. Okay. So this will become 5 into differentiation of x square, which is 2x. So that will become 10x. Okay. Is this clear now?
Yes, sir.
Yes, sir.
Okay. So the general principle here is that if I'm differentiating a constant multiplied by a function, where c is a constant, that becomes the constant multiplied with differentiation of the function. So this principle I'm applying in this example over here. Okay, so now any function of the type some constant into x to the power n, we can differentiate. Its derivative or differentiation will become how much? It will become c into n into x to the power n minus 1 on differentiating. Got it now? Hope this is clear. Okay, so people, with that we come to a conclusion of today's lecture. Okay, now what I'd like you to do is like also go through the examples, or rather the assignment sheet one that I've given earlier once more. Okay, after you revise today's lecture, go through that assignment once more, and if you have any doubts in any of the questions now, there's a possibility that with today's lecture's revision you'll be able to resolve the doubt yourself. Otherwise I will be solving those for you in the next lecture. Okay, you can also send me your doubts on WhatsApp. If you have any particular questions, you have doubts, and you can send me on WhatsApp, or if you've joined the Discord platform, you can post your doubts in the doubt room in physics in the Discord platform also. That's also a very convenient place because your doubts will be there for you to see in future also. Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Thank you, sir. Thank you, sir.
Bye, sir. Thank you.
Thank you, sir.
Okay, people. Bye.